was looking at the NAD plus NADH reaction. So we're still in chapter 15, and what we're summarizing now are 3 primary molecules. Okay, we're going to look at NADH, FADH2, ATP, and coenzyme A. Okay, and what their kind of general roles are. They're largely part of the energetics of your reaction. So our NAD plus and NADH was used to do what? So if we balance the reaction, that might help us. What do we need to add over here?
Nitrogen.
Okay, so this is the part you missed.
It was the E.
Yeah, so let's go simple.
Yeah.
Let's do the simple first, and let's ignore what biochemistry says. Let's balance this as we would as real chemists. Okay, is it just H?
But not the hydride or whatever.
It has to be hydride because our charge has to balance that. So we're actually adding H minus. Right. So in the course of this reaction, what happened to the number of hydrogen bonds to our NAD?
Increasing.
It increased, which means the species was?
Reduction.
It was reduced.
Woohoo! All right.
Okay. So NAD plus is being used as an oxidizing agent because it causes something else to be oxidized. So at the same time, it is reduced. If we used NADH, we could use NADH to then be a reducing agent because it itself would be oxidized to become NAD plus. Okay. And when we talked about it, we said, okay, we need to look at the overall structure. So we've got this big nasty structure for NAD. Okay. So we have a nicotinamide, which is a nucleotide. It's a modified nucleotide, but it is a nucleotide. And we have adenine, which is also a nucleotide. So in NAD, we have 2 nucleotides. Hence, nicotinamide adenosine dinucleotide. N and A are both nucleotides. So it's a bit of a repetitive name because we're saying nucleotide, nucleotide, dinucleotide. Okay? But that's really kind of where the name is coming from. Okay? And all we're then adding to this is a hydride. Now the question becomes is where do we add that hydride? Okay, well, the textbook has nicely colored that in so we know bulk where that's happening. Okay? And that's really happening at what's labeled as carbon 4 in that diagram. So what ends up happening is we can take a hydride from somewhere that can come in and attack that position. That then causes this pi bond to break, shuttle around, and we can move electrons to the nitrogen. Okay, well, why is that attack even feasible? Well, it's feasible because that nitrogen. What is the issue with that nitrogen right now?
Has a charge.
It is positively charged. Nitrogen doesn't particularly want to be positively charged. So it is helping to polarize that ring such that hydride can come in and do the attack to give us our reduced form. Okay? One of the things that Jimmy started to ask about towards the end of class, if not after class, okay, well, he started to make comments about the ring and it being aromatic or not. Okay? This ultimately comes from second semester OChem, which you may or may not remember. So in our rules, determining aromaticity. So aromatic structures are incredibly stable. So most reactions will strive for aromatic structures. One of the things that makes them aromatic, so our classic example would be a benzene ring. Okay? So we need a ring, and each of the carbons in the ring must have a p orbital. So this comes back to hybridization theory and all that fun stuff. Okay, well, each of those carbons will have a p orbital because that's what's making the double bonds, the pi bonds. Okay? So if we have an aromatic ring with p orbitals all the way around, and do you remember the next rule?
No.
We need the proper number of pi electrons. How many electrons are in the aromatic system? Okay, well, we just said benzene is aromatic. How many pi electrons are there? 6. So if we have 6 pi electrons, we have an aromatic structure. So if we have all these conditions met, we have an aromatic structure. If we take a look at the blue structure, okay, do we have an aromatic structure? Well, we have 2 4 pi electrons. We run into a weird rule here, which you might remember from OChem, and I'm doubting you remember, we can count the lone pair. Okay, you can count the lone pair on an sp3 atom. So it has to have 4 groups of electrons, and it does. So I can count that lone pair. So I have 6 pi electrons. Okay. So why is this structure then not aromatic? Well, what's our other rule? Every carbon must have have a p orbital. If we take a look at the carbon where we attached our hydrogen, there is no p orbital. Okay. The hybridization of that carbon is sp3. There is no p orbital to do resonance through, which then means that structure is not aromatic. Okay. So while putting the hydride in stabilized the nitrogen, got rid of its positive charge, we then also undid or removed aromaticity. And now our structure was like, well, shit, I don't want to be in this non-aromatic state. I want to go back to being the other thing. Okay, so what happens in our red structure, or pink structure, I guess? Is it aromatic? Well, if we go through and look, what do we have as our basic skeleton? We have the benzene ring. So we start aromatic as NAD+. We can add the hydride to help stabilize our nitrogen, but then that destabilizes the aromatic ring. Okay? So this is actually one of the reasons why NAD+ works, because in one direction we can stabilize it, but it destabilizes it. The other direction we can stabilize it and destabilizes it. So I have some competing effects. Those competing effects are going to be dependent on what's around it. If there's a lot of hydride floating around, it's going to push the NADH. So we end up doing almost a Le Chatelier equilibrium kind of dynamic on this. Okay? So that's going to dictate which state we're in. Okay? This also works great because then that NADH can pick up that hydride, move somewhere else, and dump the hydride onto something else. Okay? So we have a way to mediate and control the transfer of electrons from one atom to another, or one molecule to another. Okay? And ultimately, that's the big deal, is that we're transferring electrons, which is why when you look at how it's typically represented, you see this nasty equation, 2 electrons plus 2H plus NAD plus goes to NADH, whoops, I started drawing N, plus H plus. And so what they're trying to do in that representation is show that we're taking electrons and we're dumping those into the structure. Yes, we are also picking up an H plus. Okay? But that's the emphasis that we're trying to use with our NAD plus NADH couple. Okay? Is we're trying to show that we can transfer electrons, and that's why they use that equation. We're drawing attention to the fact that we are transferring electrons, okay? Not hydride. Because hydride is incredibly unstable, and that's not an easy structure to generate. Okay? In fact, we would never see hydride floating around in our bloodstream. That would be really problematic. Okay? When we generate that hydride for this reaction, and electrons are just as reactive, okay? That hydride is being generated very, very locally, and the NAD plus is being used to pick up that hydride immediately from another structure. Okay? It's not just hydrides floating around, oh, there's NADH, or NAD+. Okay? The NAD+ must immediately come in and interact. Okay? Which brings up an interesting point. We said that our hydride attacks at position 4. Why did it not attack at any one of the other positions? Okay? There's our answer. Okay? The other positions that would be valid would be our 2 and 6 positions. We won't get into why those are valid. We don't need to understand that. But those are also valid. Why do we end up picking the 4? Well, reconnect. Come on. I cleaned it up so we could see it. Maybe. Okay, I'll just keep talking. I pointed to the 6 and 2 positions. And yeah, now it's freaked out and undid everything I've drawn. Okay. We've got our 2 and 6 positions and our 4 officially that can all react with the hydride. Why does the 4 react preferentially? Well, one thing to take note of is this bond between the nitrogen of our nicotinamide and our ribose sugar. What is interesting about that bond? I know it's kind of a weird question. Look at all the other bonds in our structures. It's one of those things that is so obvious, you're like, you can't possibly be saying that.
So not, okay. I was gonna say non-polar, but that can't be it.
It's actually a polar bond.
There's a way. Like
Nitrogen
there's a group and it's kind of like.
It's a really long bond. Why are we showing this as a really long bond?
It doesn't want to have anything to do with the.
Nope, the bonds are all going to be relatively close to the same length. So why are we showing it as this stupidly long bond? What is the rest of the molecule doing? It rhymes with something.
nothing.
Nothing. It's doing absolutely nothing. So what they're doing is drawing that extra bond so we can separate out the nicotinamide so we can keep our focus on that because that's where the chemistry is occurring. Okay? So they extended that bond length so we can see it easier and kind of ignore everything else. Notice that when we look at the next structure, they completely ignore it. Okay? They're making at least a nod to chemists and saying, yes, there is a structure there, but we don't care about it, so we're going to stop looking at it. Okay? They're showing that long bond to get that structure further away. If we try to drop that down with the same bond length that we've been using on the rest of that sugar, where does that carbon, where does carbon 6 and 2 start overlapping? Starts getting really darn close to that ring, and it makes it confusing to look at. Wouldn't be able to see and understand it. But that addresses the issue that you were saying. Why is 6 and 2 less reactive? Well, they are so close to this, can I get a hydride into that position? No, there's too much junk in the way. There's a steric blocking that prevents the hydride from getting into the 6 and 2 positions. Okay? So our steric blocking just means there's, for lack of a better descriptor, shit in the way. Okay? 4 is much more available. So I can take that nicotinamide and I can just kind of aim that 4. It's still got a little bit of blocking, but it's not as bad as 6 and 2. And I can just aim that 4 carbon out there where my hydride's going to be coming in and say, hydride, jump on. There it is. Okay? It's an easier position to react. Okay? There are electronic effects that you could look at, but that's not going to be as important for what we're trying to deal with. So that makes sense? So let's look at a potential reaction here. Okay? We've got a reaction shown on top. Okay? What type of reaction is happening in that top line? You can get a lot of different answers on that one. It might be help if we got rid of those lines and turned them into bonds. So I can't get rid of the lines perfectly. But what I can do is, or the dots, but I can draw in lines over the top.
Are you looking for like oxidation? Or
There's an interesting point. Is it an oxidation reaction?
yeah,
How do you know it's oxidation?
losing hydrogen?
We lost hydrogen. Or
We lost like
Increase the bonds to oxygen?
we increased the bonds to oxygen. We started with one bond. So we look at our carbon, it had one bond to oxygen. In our product, that carbon has 2 bonds to oxygen. The other option, you referenced the hydrogens. There are 2 bonds to hydrogen from that center oxygen. And in our product, there is 1 bond. So both of those lead to a conclusion that that was oxidized. Okay? Well, what did we end up actually kicking out of this? So let's ignore what our textbook has actually drawn through for those pieces. What was lost from the structure? If I wanted to now balance this.
2 hydrogens.
2 hydrogens? Yeah, okay. Explain those 2 hydrogens to me a little bit more, because it's not 2 hydrogen ions, right? Where's your first hydrogen?
Oh, 2 hydrogens? Wait, the first hydrogen is below the carbon.
Okay.
It took, wait, did it take its
There's an interesting question. Where's the other hydrogen?
next to the oxygen?
Next to the oxygen. Okay. I would argue the hydrogen that I've got red boxed is not going to be particularly easy to determine. Okay, that's a more difficult bond to see what's happening with. So let's look at the blue box hydrogen. The electrons associated with it are between the oxygen and the hydrogen. Where would we expect those electrons to go?
to the oxygen
Why to the oxygen?
because it's more electronegative.
It's more electronegative. Which then means, what do we have on this hydrogen?
No.
Just
no electrons, just protons, I have H+. What about the red hydrogen? What happened with the electrons in that bond? Well, now that we've done the blue one, maybe this will help. How many electrons would now be around our carbon? Well, the left bond is 2, 4, 6, 8, 10. We've exceeded the octet. Carbon can't have more than 8 electrons around it. So what has to happen?
Hydrogen takes it.
The hydrogen must take the electrons with it. So instead of it being ejected as H+, it gets ejected as H-.
So you have a positron.
Right.
Is that what that's called, positron?
Positron is a positive electron, yeah, which is nuclear radiation. So ignore that. Don't worry about it. Okay. So H+, sure. Our solution can pick up an H+. That's fine. But H-, how stable is H-?
No.
Not stable at all. This reaction will not occur because we cannot eject H-. Okay? Something needs to pick up that H-. Well, in biochemistry, what's that something? H- can't be picked up by water. Water has electrons. That's electrons and electrons. Hydroxide, more electrons. That's OH-. A minus and a minus, even worse.
So an acid, basically.
So an acid is a potential possibility. Okay. Was there a species that we say talked about on that previous slide and is on the bottom of this slide?
You're just NAD.
Oh,
NAD is gonna grab that.
NAD plus can pick up that hydride
wow, that was bad.
Like, I don't know.
to make our NADH. Now we have a stable structure. H- is not particularly stable. Is that really cold?
No, it's my allergies have been acting.
Oh, okay. Okay. We now have our NADH. Now the reaction can occur. Okay. Why is this a relevant reaction? Well, after spring break, did you happen to next morning feel like crap? Some point after spring break, you're like, man, that was one hell of a bender.
No, I felt great.
Oh, okay, well, thanks. What do we have as a molecule on our left? CH3, CH2, OH, that compound's known as, there's, no,
Oh, methanol.
try
Or
again.
Ethanol.
Ethanol, also known as, colloquially in our standard language, particularly during spring break, alcohol. All of our alcoholic spirits need to be purged from the body somehow. How do they get purged? We need to improve their water solubility so it can help leave the body easier. To do that, we oxidize them all the way down to carboxylic acids, which requires 2 oxidative steps. The first oxidative step takes it to an aldehyde. What's the issue with aldehydes? What's a famous aldehyde you may have heard of?
Formaldehyde.
Formaldehyde. What do you know about formaldehyde?
It preserves you when you're dead.
Yeah, it preserves you when you're dead. If you tried to drink it while you were still alive, it makes you dead so that it can preserve you better. Okay? Extremely toxic. Okay? This is not formaldehyde because it has an extra carbon, okay, which changes its reactivity around, actually makes it easier for our biochemical molecules to grab a hold of and oxidize further down. But the aldehyde presence is actually toxic. So the buzz you're feeling and the headaches afterwards are due to the byproducts of ethanol degradation. That aldehyde is what's giving you the headache. Okay? As we continue to process that, we can turn that into an acid, and that's much easier to purge from the body. Okay? So it's an important process. It's how we're now feeling so bright and awake and not hungover.
So how come in your notes you put 2H+?
So now the question comes back as to how are we going to go through and look at this reaction. So what we addressed were the pieces and how they actually shifted. But just like we did with the previous slide, okay, you'll notice that they go through and they say, well, it's H plus and 2 electrons. Okay, well, in that bottom case, what do we have? We have NAD plus going to NADH. right? And our initial assumption was it was H minus plus NAD plus goes to NADH. Okay. Well, what was the goal of NAD plus and NADH? To transfer electrons is ultimately our story, is it transfers electrons. Do you see electrons? No. Okay. So what does a biologist who can't or doesn't want to or doesn't have the time to explain the chemistry
That's what they probably do.
go through and do? They say it's H plus 2 electrons. But to do that, I will need 2 H pluses
To make it.
to go through and balance everything out appropriately, and I also end up with an H plus over here. What's the result? If I now add these two equations together, what happens to the 2 electrons? I got one on the reactant side and one on the product side. They cancel out. Okay. So we can do some equation balancing as long as the equations are obvious, and we can go back to this, oh, it's transferring of electrons. Okay. How does it transfer those electrons? It's going through a hydride. Okay.
We're just
But
jumping over.
biology students that have no chemistry understanding, have no idea what hydrogen is, much less H minus being different than H plus. So they try and be as consistent as possible, and then also add to the memorization ability. I don't want you to remember it's a transfer of a hydride. I want you to remember it's transferring electrons. Because ultimately that's what it's being used for, is transferring electrons. But it's transferring through another step. Okay, does that make sense? Okay. Questions about our NAD plus or NADH? Okay. What's this big old nasty looking thing? You can cheat, it's up on the board.
It's a bind.
It's FAD. Okay. Flavin adenine dinucleotide. Okay. We have the adenine nucleotide. Okay. One of our definitions of nucleotides, or this fits the definition of a nucleotide, the isoalloxazine, okay, is technically a nucleotide. And it is connected to a sugar. So what we end up having, again, are 2 nucleotides. But the nucleotides are different than NAD. Because in NAD, it was nicotinamide. Well, what is this one? We end up referring to this one as the Flavin nucleotide. Okay, well, Flavin begins with F. Adenosine begins with A. I have F and A nucleotides, so I have 2 nucleotides. I get Flavin adenine dinucleotide. Okay, so same thing, same idea. Okay, well, what is the goal of FAD? Okay, FAD ends up doing the exact same thing as NAD. Okay, so it will also transfer electrons. It can also do protons as well as electrons. So it has a slightly different function. Okay, if we take this a step further, what's the relative size of FAD in comparison to NAD? It's a lot bigger. Okay, what's going to happen to something that's bigger? Exactly, it makes it more difficult. It's going to move slower. FAD is not used to transfer electrons across large distances. It's used to transfer electrons across very short distances. So it's typically folded into an enzyme, and it'll still do the same thing as NAD plus, but in its process of functioning, okay, it's only going to move very, very short distances. Typically, the FAD will do its little reaction and then transfer its electrons onto NAD. So that NAD can then go off and transfer those electrons somewhere else. Okay? So our FAD tends to be much more localized, enzyme bound almost. It's not covalently, but it tends to be very much localized in an individual area. Okay? So, interesting features though. You'll notice that it says FAD, not FAD plus. Well, why do we not have a plus? It doesn't have a plus. That's why we don't have a plus. Okay? So that's interesting, but its still goal is still to transfer hydrogen. So what would happen? If we go to FAD, Okay, if it's going to transfer electrons, what's going to be our result? We might expect FADH.
H.
But remember, the whole point was to transfer electrons with it.
No.
So it can't just be FADH if it started as neutral. What would it be?
Well, I looked, so I know.
DH plus.
2.
If we say H plus, then it didn't gain electrons. It needed to gain electrons, so we could just say FAD minus, or FADH minus. Okay? One of the big characteristics differences between FAD and NAD is that FAD transfers protons as well as our electrons. When we dealt with the NAD, we still started with 2H plus, and then when we looked at our balanced equation, we ended up with H plus just floating off on its own later. Well, why the hell did we throw that in there? Because it was kind of important in the overall transfer for that reaction. FAD changes this up. It will still transfer the electrons in the same pattern as NAD will. Except instead of accepting just a hydride, it will accept the hydride and the hydrogen ion. So we get FADH2, where one of those H's is a hydride and the other H is the H plus. Right? So we get two big pieces, or not two big pieces, but we end up transferring all of our hydrogens all at the same time in this case. Okay. I don't want to stand behind you. Stupid desks. Okay. So, some other interesting features is FAD has the ability to transfer electrons singly and paired. In NAD, it was a dump of 2 electrons straight into the system, and that's how it worked, directly through a hydride. Okay. FAD can do this in a radical mechanism. It can accept a single electron one time, and then in a later step, accept another single electron. So it still gets the net effect of gaining 2 electrons, but it can break it down into individual steps, right, which is kind of a neat feature. You'll notice that what we're looking at now, we got rid of the bulk of the molecule, because the bulk of the molecule doesn't do anything. We're again looking at the piece that actually happens. Okay? And as another big hint, they've already started to go through and highlight electrons that are going to be shifting around on you. Okay? Remember, we are transferring H minus, if we're going to do it as paired, and H plus. Okay? So where could we dump that H minus?
Well, we know the nitrogen.
If we dump it on the nitrogen, then what happens to the nitrogen?
Positively charged.
Try
No,
again.
it doesn't. It breaks the bond with carbon.
It would have, so that's the idea, is to see what would happen if that occurred. Okay, and actually, I want to switch that up, because I don't like that mechanism. Okay, we're going to start at the bottom. Okay, nitrogen, nice of them to show this for us, has 8 electrons around it, which means there is another pair of electrons there. It is a lone pair there. That nitrogen can share electrons with the H plus. Okay. But then what happens to the nitrogen?
It becomes positive.
Becomes positively charged. Does it want to be positively charged? So what does it need to do?
Delocalize the charge.
It needs to somehow steal electrons from another source. Well, if we look at our structure, we have a double bond right next to it. So what could it do?
Take some from
It could take the electrons, one of those pairs, and put it on itself. And we end up with now back at our neutral nitrogen. But then what happened to our carbon?
No, it's not happy.
Now it's missing electrons. Well, crap. If it's missing electrons, it wants electrons. So where does it get electrons from?
Carbon next.
It doesn't.
It can get them from the carbon next to it. So it takes those electrons down.
And it pisses off the nitrogen.
But then the nitrogen is way outside of its octet, and that's even worse than having the carbon outside of its octet. So what happens?
And then it grabs on.
Our hydride can share its electrons in. The net result is what happens to the overall charge for FAD.
Nothing.
Nothing. It stays neutral.
Happy. Yeah.
Okay? Because it donated electrons out, but it also accepted electrons in. So the result is we start with our FAD, and we end up going to FADH2. Okay? In that process, I technically gained H plus
And H minus.
and H minus. Okay, but again, back to trying to explain to somebody that doesn't know any chemistry, what's this H minus versus H plus, we end up saying, well, that's actually going to be 2 electrons and 2 H pluses.
Gotcha.
Okay, so it's still the same pattern that we've been seeing. Okay, it's just a question of how we get those electrons in there, and what is potentially easier to explain with to someone with no chemistry. Okay, same overall reaction, but you'll notice that in the end we end up with no excess H plus floating around, because FAD can scavenge both the hydride and the H plus. Okay. This could likewise be done in a radical mechanism. Don't stress on this, but we'll real quickly show an attempt on this. That means instead of dumping in H plus and H minus, I would dump in radicals, which means a single electron. This becomes massively more complicated of a mechanism. Okay. So we're taking a single electron from our double bond between the nitrogen and carbon, and we're moving that out to make a single bond between our nitrogen and hydrogen. We take the other electron that was in that double bond, move it into the space between our carbons. We now have half of a double bond. Okay? So the other carbon will take one of its electrons in a double bond and shuttle it in to finalize that double bond. But then the nitrogen's single electron that was in that double bond can then come out, pick up the hydride. Okay? And remember, this could happen stepwise. This does not have to happen all at once. Okay? So what we just happened to show was it all at once. Why would it be able to deal with this stepwise? Okay, so the result out of all, let's say we erased that step, is we'd have a radical there. Let's see, what did they give me at the end? Kind of a mess. How do I want to do this? There's a line, 2 lines, there's a line. Okay, and it officially has 2 electrons, another lone pair. Okay, we now have that radical nitrogen. Why is that okay to form?
What a mess. Holy cow.
Yeah, we have not thousands, but lots of different ways that that radical can be resonated through the structure. If we have resonance,
It's happy.
it's happy. So we can stabilize it. Why could nicotinamide not do this? Well, nicotinamide doesn't have as much of a ring structure. We can actually resonate all the way out to this side as well.
Goodness gracious.
Yeah. Okay. So we get resonance coming out on this side and kind of through the middle there. So much resonance can stabilize that radical, allowing it to exist for long enough to be worthwhile. Okay. And that's why FAD can go through a radical process. Okay. Because it has that resonance stabilization. Without that stabilization, we don't get the radical. We get back to NAD. It has to happen all at once in the transfer of paired electrons. Okay? So kind of a neat molecule in that respect. Next big one we encounter, and we'll talk about some of the details on this just because it does show up in your homework, is ATP. So ATP can be used to store energy. So the question becomes is how and why does it store energy? So we've got our reactions shown up top so that we can go through and process what's happening with those. Okay. It requires energy to convert ADP plus phosphate to ATP. So why would it require energy to do that? So this is going to come back to, well, how do we define our energy? Sorry, didn't mean to do that. Our energy is delta G. How do we solve for delta G? What could we look at? It's not like we talked about it at the beginning of the semester or anything.
Oh, wait, so you're talking about the delta H
There it is.
minus
T delta S. Delta H is our bond energy. What was delta S? Entropy, or a measure of our disorder. Okay. What happens as we go from ADP to ATP if we look at our disorder? It becomes less disordered. Is that a natural thing to occur? No, that is very unnatural. And we can see that because our delta S would then become positive, or sorry, negative. Okay? If we plug that into our equation, what does delta G then become? If we ignore delta H, if we have a negative delta S, what would delta G become?
Negative, and it can't be. Wait.
Oh,
You said
look
if
at your
we're
math.
Delta H.
If we ignore delta H,
Oh, it's positive because it's minus.
it becomes positive. And what do we know about a delta G that's positive?
Then it's not. It requires energy. It's not.
It's a non-spontaneous reaction. That is not an easy reaction to occur. We have to put energy in. Well, if we look at the equation, that's exactly what happens. We have to put energy in to get to ATP. The entropy helps to explain that. So we can look at the entropy decreasing in the system to make ATP. Or if we looked at the reverse, what happens if we convert ATP to ADP? We get energy out of the system. Why? Because we become more entropic. We have an increase in entropy. Okay? So we can use our delta G expressions and what we understand of entropy to do some predictions there. Okay? There's another thing that we can look at that kind of has to do with that bond energy. What we've got shown on the far right structure is what?
ATP.
Dang it, I was hoping you didn't see that. We have ATP. How do you know it's ATP?
Because there's 3 P's.
Good answer. That's what I was hoping for. We have 3 phosphates. Okay? Let's convert this into ADP. Okay, so that's a negative, and we'd end up with So the big change is that we now have this phosphate out there. The rest of that structure, ADP, is just a smaller version of ATP. So let's not worry about that piece. Let's worry about the piece I've got boxed in blue. What can you tell me about that piece? I know, really big question. We have 3 potential resonance. Actually, I think it's going to come out at 4 resonance. What does that mean the stability of that molecule is? Very, very stable. Okay. What do reactions do? All reactions do this. Other way.
They want it less stable.
They always want to go to a stable form.
Oh, yeah.
Okay, we always want to go to a lower energy form. Well, if I've got 4 potential resonance, well, that's pretty stable. What would happen if it hadn't been removed? So we could look at our phosphate still attached, our ADP. How many resonance do we get over there? 3. Which is more stable? 4. So what's going to happen? It wants to kick that phosphate off because the phosphate is lower in energy due to more resonance. Okay? So when I kick the phosphate off, because it's now lower in energy, I have to see that energy come out. There's the formation of more energy. Kind of makes sense? So there's a resonance effect that helps also explain this high storage of energy ability. Okay? I seem to think there was another one, but I can't remember what it was. Okay, so if you see the question in your homework and you can't figure it out, just send me an email. Okay, but those are the 2 big ones. You're looking at entropy and you're looking at that resonance stabilization of the phosphate, helping us release energy in the transition from ATP to ADP. Make sense?
What's the energy?
Huh?
What's the energy?
What is the actual energy value?
Like, what is, I mean, because, so it breaks, the bond breaks, but is it like transferring electron, like how is the energy?
So that's a good question. What is it doing with this?
Because they're
So
using it.
in FAD and NAD, you could say what it was doing. It was transferring electrons. Well, do we have an electron transfer here? No. Really all ATP is doing is transferring a group and doing a substitution reaction. Okay? That group does a couple things. Number one, it can ionize the molecule. If it becomes ionic, it's now more reactive. It changes some of the intermolecular forces. That molecule can now potentially do other things. Okay? Whereas before it reacted, it didn't have that access. Okay? The other thing is that that phosphate group still wants to break off of the structure. So I've now put a phosphate onto my structure, which puts it at a higher energy state, and now what happens? It wants off. That can help drive another reaction. Okay? The electrons on those oxygens want to be pulled towards that phosphate, into that resonance. That helps polarize the original molecule. Okay? So one potential example is looking at our glycolysis reactions. We can take ATP, that reaction should be flipped. Okay? We can take ATP and react that with glucose. Oh man, this equation is just horrible. Okay, so we're just going to abbreviate it this way. So this is glucose. I'm just going to write as G. If we take glucose plus P for phosphate to glucose phosphate, it's the very first step of glycolysis. That reaction on its own, extremely endothermic. Okay, very large positive delta G. Okay, not a favorable reaction. Phosphate wants to be on its own. It wants the resonance. Okay? So I can't just take a free phosphate and dump it on glucose to get glucose phosphate. It's not going to happen. So what I can do is I can run another reaction simultaneous to that one. What I will do is run ATP going to ADP plus phosphate. Well, that reaction, very exothermic. That is now such a high energy reaction that it overwhelms the low energy or the reverse low energy reaction or the glucose phosphate reaction, and it can facilitate the dumping of the phosphate onto our glucose. Okay? These have to happen right next to each other. Okay? Because ATP going to ADP and just releasing free phosphate into the solution, well, now where did all that energy go? Into solution. We heat up, we get hot. That's about it. If I run those reactions close enough to each other, the energy released by breaking that phosphate off can be immediately used to produce or help form the glucose and phosphate bond in that other reaction. Okay? So it's kind of nebulous in where does that energy necessarily disappear to? The enzyme is using that energy, the pop off of one, to kind of force it onto the other. So if we bring these things close enough to each other, okay, you can almost think about it like an ejection. ATP goes to ADP plus phosphate, and it launches that phosphate out, which means more energy because it's moving faster. Okay, the enzyme takes it and says, okay, ATP, you sit here. Now hold your horses for a second. Now glucose, come over here. Okay, now ATP, go. Launches the phosphate, smacks into glucose. Glucose goes, oh, now I'm attached to the phosphate. That hit me too hard, I now have a bond. Okay. Really crude way of looking at it, but that works. Okay. It's forcing that reaction to occur. It's giving us the proper orientation and energy, motion, to be able to cause that bond. Okay? And every time we use ATP, that's kind of what's happening. Okay? The enzyme, ATP will hold onto it for long enough that the enzyme can grab a hold of it, put it into its perfect position, and say, okay, now I want you to kind of just flick, cause that phosphate to pop off, and it moves off with enough energy and now directional force, because the enzyme is holding it there, to react with whatever particle we're putting it on. Same idea then happens with glucose phosphate. I now have a very high energy bond. What happens if I kick off that phosphate? I'm going to release more energy. Okay? It's going to be less energy than I started with because it always drops. Okay? We can't ever go up. That's what the sun does for us. Okay? And eventually the sun's going to run out of energy. Okay? Kind of makes sense? Okay. Why use ATP as the currency? Why not use glucose phosphate? Glucose phosphate will release energy. Why don't I use glucose phosphate everywhere in cells?
Because it requires energy to become glucose phosphate.
True, but why didn't I use my energy source, say from the sun, to make glucose phosphate instead of to make ATP? Because I still have to use something. I still have to use an energy store.
ATP has more energy than glucose.
There's an interesting question.
Doesn't it?
It does. Why not use a particle that has even more energy than ATP?
Because we don't have it.
When you go to the bank or when you go out into the store and you use cash, assume you're using cash, how often do you give them, what do we got, a $1,000 bill?
Never.
Why not?
It's a waste.
Okay. That currency is too high a value. How often do you just give them pennies?
It's too hard.
It's too low of a value. We'd have to bring too many in. ATP, the energy released in the formation of ADP from ATP, happens to be a relatively perfect energy value. Probably like a $20 bill, roughly. Okay? When you go to pay for something with cash, very often you use 20s. Okay? It's a not too high value and a not too low value. Glucose phosphate is a little on the too low end. Okay, why else? Glucose is kind of big. We could start bringing in size effects. We would want something that can transfer the energy and isn't so massive that it can't move around the cell. Okay, so that's one of our big reasons on ATP. It is the perfect currency value that we can use it to get out to various places. If I need even more energy than ATP can have stored, I can use multiple ATPs. Okay? If I need to buy something that's $50, I can use 3 20s. Okay? So that's kind of the idea behind that. There are a variety of other phosphate-containing compounds. So your textbook lists out a whole bunch of them. And you can see they're delta Gs. Okay? The delta G for kicking that phosphate off, a lot of those are negative. Yeah. And you'll notice ATP is kind of sitting right in the middle there at 30. Okay, there's the exact energy value, our 30 kilojoules per mole. Okay. We could go up a whole lot higher to 62 for our phosphoenol pyruvate. We could go a lot lower to our glycerol 3-phosphate. Okay. Why do we not use those? Those aren't providing either enough energy or too much energy for the process to occur. If we go too much, what ends up happening? It'll still power, say, making glucose 6-phosphate. What happens to the rest of the energy? It gets left as heat. So if we use something higher in energy than ATP, we can't use all of that energy at any given time, so we'd use it to do whatever reaction we have. The rest of that energy gets dissipated as heat because it can't get consumed. Okay. So ATP happens to sit at a perfect place for that. Okay. The last big one we'll look at, which will pop up a couple times, in a variety of different fashions, is Coenzyme A. Okay? It is an activator. Okay? Just kind of an odd statement to go through and make and now include on the slides, but I'm going to blame the textbook because I'm stealing most of the textbook slides. ATP is an activator as well. It does the same thing. Okay? So an activator is just something where we change the structure that now makes it more reactive so that it can react further on down the line. That's it. Okay? Coenzyme A ends up doing the same thing. So we have a reaction A plus B going to AB. Okay? That reaction is not favorable. So what does that mean our delta G will be? It should be positive. So with respect to 0, it should be greater than 0?
Yeah.
Okay.
And we just did the opposite thing. It's like,
No. Positive is bad, negative is good.
positive G
Is bad.
is non-spontaneous.
Non-spontaneous.
Okay.
Okay. So if we look at the reaction A to B, or A plus B to make AB, If it's positive, that reaction's never happening. Okay? Or not at any reasonable condition.
Or not by itself.
So what the enzyme, or what some of our enzymes can do, is they can bring in other particles to help change the energy around to allow the reaction to occur. This is where ATP can come in. We can bring in ATP to cause one of the energies to shift up high enough where we can cause the reaction to occur. Coenzyme A can do something similar. So coenzyme, in this case, the coenzyme we're just using as a general term, can react with, in this case, A, for the example I've got, to form the coenzyme bound to A. What we're saying is that that bond now is exceptionally high in energy. Okay? That bond is ridiculously high in energy, which then means when I react that species with B, okay, that bond is dying to break. B can come in and say, okay, fine, I'll let you release some of that energy if you give me some of it so that I can partner up with AB. Okay? So really what we're saying is the delta G for that next reaction, or for that A plus coenzyme, that is now stupidly less than 0. Okay? So that when I add the two equations with each other, the overall delta G for the reaction is also less than 0.
So that's basically what we just heard.
That's what we did with ATP. It's the exact same thing.
With the glucose.
Okay. Except in this case, we aren't using something known as, or in those cases we were using ATP as our energy source. In this case we're using something, a different molecule, okay, a coenzyme. All a coenzyme is something that can help the reaction occur, or is necessary to help the reaction occur in the enzyme. Co being with enzyme. Okay. The big example that we end up using is one known as coenzyme A. That's the structure on our next slide. Okay. We got a
Coenzyme A
it's-
is found first.
uh,
Or is there-
good question.
Just throwing that out there because it's.
I would bet so.
Okay.
I'm not positive, but I would bet so. I would bet it was one of the first enzymes discovered. Okay. It might have actually been somebody was studying an enzyme function and noticed that it needed this extra piece, and they said, oh, this is the first piece for this one, I'm going to call it A. And then as they continue to work, they found other things in other places, so that's where they use the general term coenzyme. Okay. Because if you look at the pieces of it, you have a thioethanolamine, beta-alanine, pantothenic acid, ADP. None of those scream A to me. Okay. So it is likely an order of when it was discovered. Okay. Within all of that, really the only thing that is important is the sulfur at the end. Okay. And hopefully Jimmy comes back and watches this video so that he can then complain that I'm yelling at him for not being here. Okay. Because I at least know his organic background because he had me. So what can you guys tell me about the thiol? He'd have a hard time with it too. in all honesty. No, it's actually not a very, well, sort of. It is not a good leaving group from the structure of the coenzyme.
It's very electronegative, isn't it?
Sulfur's not very electronegative, but it's very big. Okay, what does that mean about the acidity of that hydrogen?
It's acidic.
It is very acidic. So that hydrogen can actually be kicked off, and I'm not sure if it's at natural pHs. It might actually not even be there. So you end up with a negative sulfur. What's interesting about a negative sulfur?
No idea.
You have a very good nucleophile. So we can use that sulfur as a good nucleophile to then attack something electrophilic, say like an acetyl group. Okay. Now back to your original statement. You said sulfur is a good leaving group. Why is it a good leaving group? Sulfur is massive. So by making this bond, I now have a very high energy bond between the sulfur and that acetyl group. This can now allow me to take a much weaker nucleophile, say like water, or even a phosphate, and that can then come in and attack, kicking out the awesome leaving group of the sulfur. So the coenzyme helps to activate particularly carbonyls to a later nucleophilic attack by a weaker nucleophile than the sulfur. Okay. Neat little reaction. And we will look at this one at least twice more this semester, okay? Because the sulfur does some kind of interesting things, and it shows up in a lot of our very large kind of enzymatic complexes. Okay? So in this case, you really just need to realize the sulfur acts as an activator, okay, making our electrophilic atoms next to it much more electrophilic. And that's because the sulfur is an excellent leaving group, and it is an excellent leaving group because it is big. Make sense? You get all that? Is there another question in there, Mike?
Well, yeah, I'm just trying to follow the chemistry, so replay it in my head. So it becomes a nucleotide that attacks just
It can attack a weak electrophile. Okay. Because it is a better nucleophile than most oxygen-containing species, okay, it can attack a weak electrophile. That then makes this kind of high-energy linkage that I've got highlighted in blue. That's high energy because the sulfur, as good as it is as a nucleophile, is almost equally as good as a leaving group. So that then allows, say, a weaker nucleophile like water or any kind of oxygen-containing group to now go in and attack that carbonyl carbon, which is our electrophile, and it can kick out that leaving group.
Okay.
So in the previous case, so that blue bond is the equivalent of the bond between A and our coenzyme. It is that bond that is your big characteristic there. The coenzyme comes in, makes that linkage, now facilitating the next step of the reaction. Okay. So in our case up here, we have A being our electrophile, and B is a nucleophile. The issue is that B is such a weak nucleophile that it won't react easily with the electrophile. So what we end up doing is reacting it with the coenzyme to make a really, really, really good electrophile. And good now means in caps and spelled all the way out. Okay. So that B, being still that weak nucleophile, can come in and react and kick out the coenzyme.
Would it necessarily be water that is attacking that? Or
Not
just
necessarily. Yeah. So, and we'll see in a couple different cases what that ends up being. Okay. Because it can be an enzyme. It's typically used in the transfer of an acetyl group. Okay. So this is an acetyl group, CH3. So what is out here could be a variety of things. It could just be water. It could be a protein. It could be an enzyme. It could be a nucleotide. Okay. It could be DNA. Because that acetyl group can now be used as a marker to say, hey, look at me, do a reaction here. It could also be used as a, hey, look at me, I'm marking something that's bad, you need to come fix this. So in the case of DNA, if we acetylate DNA, there's an enzyme that can go through and say, that's a problem. I'm going to go through and I'm going to cut out that problem and we're going to try and fix it. We'll put it back together the way it was before that happened. Okay? So we can use this acetyl group to help kind of mark things. Okay? It is also part of our natural metabolic processes, which we'll see when we look at glycolysis and the Krebs cycle.
So would this then be, like most, like, since it's not a primary carbon, would it be an SM1
It's technically, if you want to get into it, a nucleophilic addition and elimination. It does two, because you're attacking at the carbonyl carbon. So it's a nucleophilic addition, because the very first step you break the pi bond and then it's an elimination because it comes back down and kicks out a leaving group, which is second semester OChem, which is one of the reasons why I find it absolutely infuriating that the prerequisite for this class now does not include second semester OChem. That reaction is second semester OChem. Okay. So if somebody asks why, what can I tell them?
Right. I gotcha.
Okay. So this is now referencing much nicer than what I just drew up on there. Okay. If we take a look in that tiny little yellow box, it's really difficult to see what's there. Can you tell what's written there?
That's your acetyl group.
It's the acetyl group. Okay. And in this case, what are they using as their nucleophile? Yeah, I know. It's water.
Okay.
So that they can then make acetic acid. Okay. So in this case, maybe this was part of the last oxidation step in ethanol, making acetic acid. Acetic acid can now be purged from the body relatively easily. Okay. And you notice they show the giant structure there. Virtually none of that is actually contributing. Okay. And they aren't showing a mechanism, they're just trying to show sort of intermediate steps. Questions about it? Okay. So, electron transfer, ATP production, and metabolism. This is a nice kind of summary slide. You can see a lot of different pieces in here that we've already talked about. We've got catabolism and anabolism. So they're showing that big red line for. It's trying to show the difference between these. We will be looking at glycolysis. So the results of glycolysis get dumped into the citric acid cycle. But as we do glycolysis, we can also produce ATP and NADH. So when we process carbohydrates, we make energy. Not only do we make energy in ATP, but we also make an electron carrier. The electron carrier can end up getting used in oxidative phosphorylation, or the electron transport chain. As we continue to process some of the pieces from glycolysis, we also make more electron carriers. Those electron carriers can be used to make even more ATP, again through oxidative phosphorylation, also known as our electron transport chain. Okay. If we shift to now the anabolism side, notice that what we're end up using is using NADH and ATP to go through and make something. Okay. And that's our anabolic side. So we're reversing, we're now releasing that energy off. So our catabolism, what's our energy stores, okay, using them or making them, and then in anabolism, once we've got them made, use them to make something else. Okay? You'll notice that in the anabolism side, we do not see FAD. Why not?
Because that's a travel too far.
FAD was not a traveler. Okay? It's stuck in our enzyme. NAD is really the one that it does our traveling through our metabolic processes. Okay? Makes sense? Oh, I thought I was going to get way into glycolysis. Doesn't look like we're even going to get close. Still got a couple minutes. So our big summary, NADH, FADH2, and ATP. Okay? And then lastly, our coenzyme A. Those are all crucial stages that we need to be aware of. And we now have a general idea of what they are doing. What we now need to do is say, well, when and where do we use them? And we start looking at the details of those. Okay. That is now moving into chapter 17, glycolysis. So what I'll kick through here will just be the initial summary slides on this. Okay. So your textbook has some kind of pretty pictures. This would be something, if you've got some standardized pre-health tests, pretty much all those numbers you need to know. So from each of those stages, what's released, how much is released, all of that fun stuff. Believe it or not, some of those numbers are debatable. For instance, through the oxidative phosphorylation, I've actually heard 32
That's what I.
ATP. I've also heard more than that, and I've heard fewer than that. A lot of that depends on the efficiency of the enzyme making ATP, and depending on the animal, for lack of a better descriptor, the animal that sourced the ATP synthase enzyme, you're going to get varying amounts of ATP produced. Okay? So that number can kind of fluctuate. So watch out for those. It's not perfect. Most of the cases with our NAD, they don't even show FAD in this, do they? No, they don't. So our NAD and NADH ones, those tend to be very much specific for those individual steps of the reaction. The biggest one that's questionable is that last one, that ATP. All the other numbers within that, I think, are pretty firm. I don't think you'll get any challenges on those. And we'll talk about why that 32 is challenging when we get to the electron transport chain. Okay? So you need to be aware of each of those steps. Our next slide shows another picture where we see all the names, same idea. We're breaking out. This is now specifically just glycolysis. Glycolysis is really going from glucose to pyruvate. Okay? Some interesting pieces to note. When we reference this, how many glucoses are we starting with? 1. When we run end glycolysis, we end up with 2 pyruvates. This is something that's important to note because each pyruvate then moves through the Krebs cycle. So we get 2 sources of potentially metabolic processes coming out of this. Okay? And then after that, yeah, we'll actually start into glycolysis. So I will definitely stop there.